So now we're going to be looking at refraction and reflection together. I'm just going to change my cursor so we don't get that pointless circle appearing. Okay, so we've got a laser here. If I press the button, we have a beam that comes out of it, and it reflects off the surface. This is actually going from air into glass. We know that when we look at glass, we can see our own reflection, but we can also see through the glass into something else. This shows that that light can go from air into glass, and then it can come back out again. So you can actually, if I turn this off, you can actually change this to go from glass to air instead of air to glass. I can just adjust it up here as well. So it can go through air and it can go through glass, and that's obviously how we can see through windows, but we can still see our reflection in the windows. You can also notice that if we can actually click on this, and we'll notice the law of reflection, that the angle of incidence is always the same as the angle of reflection. So 24.7, 24.7, 14.3, 14.3, 29.3, 29.3. Angle of reflection, law of reflection says that the angle of incidence is always equal to the angle of reflection. Okay, that's basically the only thing you need to know about reflection, apart from maybe applying that law. So in other words, how might they catch you out with this law of reflection? Let's imagine you had a mirror here, and you would say, oh, I don't know, like maybe a wall here. This is a bird's eye view, by the way. And this is a person A, and this is a person B. They might say, draw a diagram to show how person B can see person A. Now, if you might think, oh, you see it because there's a mirror there. And so you think, no problem, I'll do this and this. Actually, that's actually pretty good. I was hoping to do it. I'm trying to do it incorrectly. Like that. And then, so that would be wrong for a number of reasons. Can you work out the reasons why I would get that wrong? I've exaggerated to make it slightly easier. But why do you think I might get that wrong? And the reason why I would get that wrong is, one, I haven't used a ruler, so the angles are not the lines are not straight, and one of the most important things you need to know about light is that light travels in a straight line. Second thing I haven't done is shown the direction that the light is traveling, so it should be like that. I'm not going to bother drawing these with a ruler right now. I will do a correct diagram in a moment. The third thing I've done is I've not applied the law of reflection. If I drew a normal here, like that, we'd be able to see that that angle is not the same as that angle. The angle on the left, the angle of reflection, is actually larger than the angle of incidence. So that's incorrect. So I'm going to actually draw another line with a line tool, and I'm going to use a different color. I'm going to use yellow, so we can see them both. And this time it's a bit tricky to make sure I get it exactly right, but I've got to try to make it so the angle of incidence is equal to the angle of reflection. Okay, that looks like it's probably going to be a bit better. So now if I draw a normal, that angle there is roughly the same as that angle. Well, it's supposed to be anyway. It's supposed to be the same as that angle there. And I would still draw those arrows like that. So that's the kind of way that they might catch you out using the law of reflection. The angle of incidence is always equal to the angle of reflection. That's reflection. Now, refraction. Refraction just means that when light goes through from one medium to another. What does a medium mean? A medium is the material that the light is currently traveling through. So that's medium A, and this is medium B. Medium A at the moment is glass. Medium B is air. But it will, it changes depending on. I could obviously I could change this on this simulation. So let's have a look at let's play around with this. If we went from air to air, there's clearly no difference. There's no reflection because it's not reflecting off anything, and there's no change in the angle of incidence to the angle of reflection. As I move, as I change medium B and make it more dense, notice that the ray of incidence, the ray of refraction, this ray down here, is moving towards the normal. Just to be clear, so as we know, so as we're clear about this, let's use a different color than that. I'll use black. This is the normal, okay? It's a perpendicular line, so it's right angles to this interface here between the two mediums, and it's drawn where the ray of light touches the medium, okay, the new medium. And we can see that as I move, as I increase the density of the second medium B, the ray moves towards normal. Can you see that? Yeah. So now the other thing you'll notice is the index of refraction, or the refractive index, is increasing as well. Okay, so it's probably more accurate to say that as the light moves from a lower refractive index to a higher refractive index, the ray of refraction moves towards the normal. Okay? Obviously, the other way around, it would move away from the normal. So if I went, if we go back to our glass, so glass to glass, clearly there's not going to be any, let's choose glass there. Clearly there's not going to be any, there's a mistake here. That says 1.5, that says 1.6. I think that's just a mistake with the simulation. Let me just pick glass. Okay, cool. Anyway, then it's clearly not going to be any refraction and no reflection either. But if I went from glass to air, it moves away from the normal. Okay, so that makes sense, right? So it's clearly going to do the opposite. Now this is where things get a little bit weird. If I go from a more dense medium to a less dense medium, or from a higher refractive index to a lower refractive index, I can get something, because if I move that a little bit further, eventually the angle of refraction is so large it goes beyond 90 degrees, which means it gets reflected back inside. So that's important. That's called. Do you know what that's called? So that's called total internal reflection. So if I increase the angle of incidence such that the angle of hang on a second. If light moves from a higher refractive index. Higher refractive index is usually higher density, but not actually always. Okay, but if light moves from a higher refractive index to a lower refractive index, then it then let's say and if I increase the angle of incidence such that the angle of refractive index is greater than 90 degrees, we have total internal reflection. Just to be clear, what do I mean by this? By greater than 90 degrees, I just mean that at the moment it's 65, but if it went greater than 90 degrees, it's not going to be able to. It means it's not getting out, doesn't it? It's just been totally reflected back inside. So this is what we call total internal reflection. Okay, so you only get total internal reflection if you're going from high density to lower density. Okay, or higher refractive index to lower refractive index. You only get total internal reflection if the if the light, you get total internal reflection and reflection also, and also refraction with all waves, but we're looking at light at the moment. We only get total internal reflection if a light wave is moving from a higher refractive index to a lower refractive index. Okay, so the next thing to learn is Snell's law. Okay. Oh dear. Snell's law. Well, Snell's law is a formula essentially that relates these two refractive indices to what the angle of refraction is going to be. So let's just if we get it like that for a moment. Clearly, if I were to increase, you can see as I increase the refractive index, so as it's closer to that, I'm going to get a different angle of refraction, aren't I? That makes sense, right? If the two refractive indices are close to each other, then we're going to have little or no refraction, right? If they're further away, then we're going to have some refraction. Okay, air to glass, we're going to have a lot of refraction. Glass to glass, we're going to have no refraction, and water to glass, we're going to have less refraction than air to glass. Okay, because they're closer together. So there is a way of predicting, of calculating that using Snell's law. So let's just do a bit of research to find out what Snell's law is. Okay, so Snell's law is saying that, in this case, it's going from bottom to top, but it's saying that theta n1 times sine theta 1 in this case would be the angle of incidence, is equal to n2 sine theta 2. Sine theta 2 would be the angle of refraction. So let's just move that over here for a moment, and I'll write it in the way that we've got here. So we'll say that. So basically, according to that, we're saying that theta 1 is saying angle of incidence, and theta 2 we can say is equal to the angle of refraction. In this case, I is equal, angle of incidence is equal to 31.7, and the angle of refraction is equal to 42.9, right? So, and we've got an N1, so N1 is equal to 1.5, and N2 is equal to 1.156, because I've got some random one there. 1.156. Okay. What it means is how much does it refract light? And we'll look at in a moment what is it, why does it refract light in this way? Why does it have this effect? But for now, we're just going to say how much it refracts light. So let's move this down for a moment. And then we'll say, well, the constant, it's in the way. Let's put it there. So concept law then, n1 sine, instead of writing theta 1, I'm going to write I is equal to n2 sine r. Okay, so now I've taken their law, I'm going to just close that window because I've got it written down already, and then we're going to see if we can use this formula to get the angle that we'd expect. So we know that theta, that I is equal to 31.7 and R is equal to 42.9. So we want to let's rearrange this formula to go n1 over n2 is equal to sine R over sine I. and then we're going to say that n1 over n2 is equal to, well, n1 is 1.5 and n2 is 1.156. So do you want to just quickly do that on your calculator and get an answer for me? So 1.5 divided by 1.156. I hope I've not made a mistake here on this. It's getting a bit complicated now, but let's hope. 1.297. Next, we're going to do. Yeah, I've forgotten to write the I there. Look. Yeah. Next thing we're going to do is going to divide sine r over sine I, which is sine r is 42.9 and I, is it's 31.7. Okay. So do you want to just quickly work out what that is on your calculator? I'll do the same. Right. So putting that through my calculator, I get not quite the same number, but that's just because there'll be some rounding error at some point. But basically the same. I get 1.295. So there we've checked it out and it matches up. So basically the n1 divided by n2 is equal to sine r over sine I. So that's Snell's law. So the only thing left to understand is why does this even happen? Why do we get this this changing of angle when it goes from a less dense to a more dense, from a more dense to a less dense? Why does it change like this? If I can actually measure the speed of the light. If I put it over there, it says the speed is 0.67 c. Well, what does c mean? C just means the speed of light in a vacuum. A lot of people say the speed of light is constant. Light never changes speed. That's not true. The speed of light in a vacuum is constant, but when it goes through glass or water or air, it does slow down. And the refractive index is actually It's actually a measure of how much it slows light down. So here it slows down to 0.67 of that speed. We know that c is equal, well, you may know, I happen to know that it's roughly 3 times 10 to the power of 8 meters per second. Well, when it goes through glass, it's going at about 2/3 of that speed. Whereas if I look at it in air, well, it's recorded it as, actually that's not air, actually that's a custom. So 0.86. So I can measure the speed there. So that means it's actually slowing, it's speeding up as it comes into this. If I click on the wave format, you can see that basically, if I pause it now, just at this junction here, this interface here, one side of the wave will get to speed up before the other side. So if you imagine, if we draw just one of those wavefronts enlarged, in fact, let's draw it over the top of this interface here. Let's draw it right at the interface there. So I'm drawing this one here, but larger. We can see the left-hand side is going to speed up faster than the right-hand side. Now, if you imagine there was a wheel on either end, imagine this is a wheel axle of a car, and this wheel starts to speed up faster than the right-hand wheel, then this is going to get a greater distance than this. And so you're going to get a sort of turning motion. At first it was going there, now it's going like that. So the reason why it changes direction when it slows down is because one side of the wavefront will speed up faster than the other side of the wavefront, and so that's why you get this rotation. The other thing I'll just briefly introduce in this relatively long video now, actually I'm going to take a snapshot of the notes we've got so far, then I can clear the screen. Yeah. Let's clear that, and I will also just pause the video while I just save that. The other thing I want to look at is if we go to prisms, this is where we get to understand how lenses work. So if I shine a light like that, it's going to if I change direction, the direction, you can see we're going to have refraction in and we're going to have refraction out, right? It goes. If we can we draw the normals? We can. Cool. It goes towards the normal on the way in. It goes away from the normal on the way out, right? Because it's going from low refractive index to high refractive index to low refractive index. Okay. Now, let's take that one away and we'll make it parallel for now. Actually, let's just put it back again for a moment. We can see that no refraction because it's going right down the normal. Okay, sine 0 is 1, so you're going to have sine 0 over sine 0, which will be 1. And so there's no it's not going to change. It's not going to change. The angle's not going to change. But if I got one of these, you can see that actually. Let's put this over here for now. Let's just put it back actually. If I go over here, as it goes into this shape, it's going to go towards normal and away from the normal. But because the angles, it actually has this focusing concept. Imagine we had a lens like this. We can imagine the beginning bit. If I drew a basic version of that lens, you could imagine it could be drawn like this. So it could be made up of a cube and then two triangles. Okay. So the triangles, I've just drawn a trapezium here. Let's get a triangle though. Same sort of idea. The top part is going to focus it down. If I rotated it that way, the bottom part is going to focus it up. And meanwhile, in the middle, that one's not going to do anything at all. So if I were to get three, I can't quite do it because when you do this, they're a bit too close to each other. So you can't get the shapes to actually represent what I'd like to just get three of these really. So I could actually, I don't think there's another way. It's a bit annoying. You would have thought it'd be a lot easier just to get three lights and then I could actually demonstrate what I'm trying to say. But instead, I'm going to have to just show you that. Imagine we've got a ray of light. In fact, yeah, that'll probably make most sense. Yeah, okay, let me just turn it off for a moment. So I'll have my basic one there. And when we got, let's just adjust that a little bit. This is obviously, a lens is a lot more curved, so the effect is more gradual, but it demonstrates the idea that when I when I do that, it focuses it there. If I do it in the middle, it goes straight. If I do it on that end, it focuses it there. So you can see they all go towards the middle. And so that's why a lens like that focuses it towards the middle. Okay, that's using refraction to focus it towards why refraction works to focus light. All right, so we'll stop that video there and then we'll look a little bit more closely at lenses, okay, because that's the bit that you're really struggling on. Is that correct?